October 2025. Two chemically anomalous visitors are closing in on the same world. Interstellar comet 3I Atlas, with its carbon dioxide-rich coma, and R2 Swan, a hydrogen-bright comet first flagged by the SOHO SWAN instrument, are both converging on Mars. Separately, each would be historic. Together, the odds defy probability, vanishingly small alignments predicted only once in millions of years. Yet here they are, arriving within weeks of each other, just as a solar blackout window begins. And this time, Mars is not empty sky. It is a planet crowded with orbiters and rovers, machines that could be caught in the crossfire if either comet fragments. Is this mere coincidence, a hidden choreography of the solar system, or something else entirely? The story begins in midsummer. On July 1st, 2025, the Pan-STARRS Survey Telescope in Hawaii logged a faint object with a trajectory unlike anything in its nightly catalog. Within days, orbital solutions confirmed it was not bound to the Sun. This was 3I Atlas, only the third known interstellar visitor after Oumuamua and Borisov. Its path traced a hyperbolic arc aimed directly into the inner solar system. Then, on September 11, 2025, an entirely different detection made headlines. This time, it was not an optical telescope, but the SWAN instrument aboard the SOHO spacecraft, which monitors solar wind interactions. A sudden surge in hydrogen Lyman alpha emissions lit up its detectors. Ground-based follow-ups revealed a brightening comet, R2 Swan. What startled astronomers was not just the timing, but the direction. Early trajectory models placed both Atlas and Swan on paths that would carry them into Mars's orbital neighborhood within weeks of one another. Individually, each discovery would have been remarkable. Interstellar comets appear once in a generation, and hydrogen-dominated comets are rarely caught this active so far from the Sun. But the coincidence of two such rare bodies in the same season is nearly unprecedented. For many observers, it was less a matter of detection and more a matter of cosmic choreography. By September, orbital analysts began plotting Mars-centered diagrams. 3I's Atlas would sweep past perihelion on October 29th, crossing just outside Mars' orbital plane at a shallow inclination. R2 Swan, discovered later, tracked toward a slightly earlier perihelion with a steeper tilt, but its outbound trajectory also intersected Mars' vicinity. For planetary dynamicists, the overlap was striking. The two comets were on different long-period arcs, one interstellar and one solar system-borne, yet their paths were due to converge on the same orbital longitude. This alignment would occur against the backdrop of a solar conjunction blackout, when Earth-based observatories lose visibility as Mars slips behind the Sun. That means the most critical weeks of approach are also the hardest to monitor. Only orbiters at Mars and solar probes like Parker and Solar Orbiter will maintain uninterrupted coverage. Statistically, the alignment is a vanishing rarity. Population models suggest the probability of two chemically active comets crossing Mars's orbital corridor within a single season is less than 1 in tens of thousands of years. Some astronomers argue it is simply chance amplified by improved detection networks. Others warn that the timing is too exact, the blackout window too precise to dismiss outright. And if the orbital choreography looked improbable, the chemistry of Atlas itself would prove even harder to explain. If R2 Swan is strange, 3I Atlas is unprecedented. From its first spectrum, anomalies dominated. Normally, water vapor outgassing dwarfs all other volatiles in comets approaching the Sun, but with Atlas, the ratio was inverted. JWST confirmed carbon dioxide production at roughly 129 kilograms per second, compared to just 6.6 kilograms for water. That is nearly a 20-to-1 ratio, unheard of in any bright comet to date. The Very Large Telescope in Chile added to the puzzle. Its high-resolution ultraviolet spectrographs detected a strong atomic nickel signal streaming from the coma. But iron, which almost always accompanies nickel in cometary chemistry, was absent. The missing iron sparked a flurry of theories: selective loss during interstellar travel, exotic formation chemistry, or even weathering under billions of years of cosmic rays. Then came a shock from orbit. The Mars Reconnaissance Orbiter, scanning ultraviolet wavelengths on August 21st, recorded a sudden flare. Atlas doubled in brightness in less than 36 hours, splitting its dust tail into multiple streams. Ground-based photometry confirmed a tumbling, slowly rotating nucleus with a period stretching beyond 22 hours, unstable and difficult to model. For many planetary scientists, Atlas represents a class of object we are only beginning to understand. But for others, the anomalies push beyond natural chemistry. Could a comet stripped of water and iron, but rich in carbon dioxide and nickel, be evidence of formation in an environment unlike any known nebula? Or, as some speculative papers have dared to suggest, could such selective chemistry point to something engineered, not born? Unlike Atlas, which revealed itself in deep sky surveys, R2 Swan's discovery came as a flare in hydrogen. On September 11, 2025, the Swan instrument aboard SOHO recorded a sudden surge in Lyman alpha emissions, the ultraviolet fingerprint of hydrogen interacting with the solar wind. Ground-based observers scanning the Virgo constellation quickly confirmed a brightening comet with an expanding tail. Within nights, its profile transformed. The tail doubled in length, its coma composition dominated not by water vapor, but by free hydrogen and cyanogen traces. Such hydrogen-rich activity so early in its inward journey caught even seasoned comet researchers off guard. Most comets ramp up only as they approach the inner solar system. Swan, by contrast, seemed primed to vent hydrogen at extraordinary rates. Citizen science astronomers became essential. Backyard observers logging tail morphology and brightness spikes provided rapid alerts that professional observatories then verified with spectrographs. Several outbursts were timed only because amateurs spotted the sudden elongation before scheduled professional sessions. The working hypothesis is that Swan's nucleus is fragmenting under thermal stress. Cracks expose volatile-rich layers, triggering sudden releases of hydrogen. Near Mars' orbit, these stresses may accelerate, raising the possibility of a catastrophic breakup event. For Mars orbiters, this could mean a front-row seat to a volatile spectacle, or for mission planners, a cloud of debris complicating operations. Which led to the next urgent question: what if these debris streams don't just pass Mars, but collide with it? Trajectory models place both comets within Mars' orbital corridor in late October. 3i Atlas is projected to pass at a minimum distance of several million kilometers, but with a margin of uncertainty that widens after each recorded outburst. R2 Swan, less massive but far more volatile, carries even larger uncertainties as its tail structure evolves daily. In probabilistic terms, the official assessments classify the chance of direct collision with Mars as extremely low, well below 1%. Yet in planetary science, even a tiny probability window is worth scrutiny. Comet Shoemaker-Levy 9, once considered a long-shot candidate for a planetary encounter, ultimately shattered into fragments that plunged into Jupiter's atmosphere in 1994. Its impacts left dark scars visible for months. For Mars, the concern is not just direct impact, but atmospheric grazing. A close flyby of a fragment could trigger visible plasma interactions, auroral bursts, and dust injection into the upper atmosphere. Such events would pose no danger to Earth, but for orbiters and rovers operating around Mars, even small debris fields could prove hazardous. As of early October, planetary defense networks are running updated simulations daily. Each new data point feeds into a narrowing corridor of possibilities. Whether these bodies pass harmlessly or interact violently with Mars' atmosphere remains an open question, one that can only be answered in real time. If either comet were to fragment within Mars' upper atmosphere, the results would be spectacular. 3i Atlas, with an estimated nucleus diameter of several hundred meters, carries an energy yield many times greater than the 2013 Chelyabinsk airburst. Scaled to Martian conditions, a stony impactor of that size could produce a dust plume visible from Earth, briefly altering atmospheric transparency for orbiters and telescopes. R2 Swan, though smaller, poses a different kind of spectacle. Its hydrogen-rich composition means fragmentation could trigger rapid combustion-like flares when interacting with the solar wind. From Mars' orbit, these outbursts would appear as sudden ultraviolet flashes, detectable by instruments tuned for hydrogen lines. Comparisons to historical events provide perspective. Chelyabinsk released about 500 kilotons of TNT equivalent. Tunguska in 1908 was closer to 10 to 15 megatons. A full-scale Atlas impact on Mars would exceed both, injecting vast amounts of dust and volatiles into the atmosphere. Speculatively, some atmospheric modelers propose such injections could temporarily modify Martian climate, thickening local haze and altering temperature gradients for weeks or months. While Earth would remain unaffected, Mars missions could face degraded communications and imaging windows. The key variable remains fragmentation. Stable nuclei pass quietly, but unstable ones like Atlas and Swan carry the potential for sudden energy release. The difference between a harmless flyby and an atmospheric event written across an entire planet's sky. But light and dust weren't the only things being tracked. Astronomers also tune their instruments for signals that might ride on these outbursts. As both comets approach, radio telescopes worldwide are listening. Facilities like the Allen Telescope Array and FAST in China have devoted scan time to monitoring Atlas and Swan during their brightest flares. The goal, to search for narrowband pulses or structured emissions that could indicate more than natural outgassing. So far, no confirmed detections have been reported, but monitoring teams note curious fluctuations in background noise floors during outburst events. Most are likely instrumental artifacts or solar interference, yet the timing raises questions. Outbursts vent gases at high speed, creating plasma interactions that can mimic narrowband spikes. Distinguishing natural plasma physics from anything engineered remains an open challenge. SETI researchers acknowledge the speculative angle. If a comet were engineered or altered, one might expect anomalous emissions during periods of stress. No mainstream papers claim evidence of this, but the debate lingers on forums and in conference-side sessions. The hypothesis remains unproven but tantalizing. Outbursts could produce signals that look artificial. Whether coincidence or choreography, the convergence of two anomalous comets on Mars has heightened interest. For now, radio astronomers remain cautious, cataloging every fluctuation and cross-checking with solar wind data. Until a definitive pattern emerges, the possibility of artificial mimicry hangs in the background, a reminder that the line between natural signal and engineered intent is vanishingly thin. By early October, the world's major space agencies had begun quietly rearranging priorities. Observers at Pan-STARRS and the European Southern Observatory reported unusual scheduling directives, blocks of telescope time suddenly reassigned to comet monitoring with little explanation. NASA's JWST slotted emergency observation windows, while the European Space Agency's Mars Express began devoting significant bandwidth to spectroscopic tracking. Even China's CNSA Deep Space Network adjusted coverage to include Swan and Atlas flybys. Citizen astronomers noticed something else. Data portals that usually update nightly with open-access comet photometry were delayed or truncated. Archival updates appeared in irregular batches, sometimes days late. Forums lit up with speculation. Were agencies suppressing anomalies or simply overwhelmed by the flood of new data? There is precedent. During the Hale-Bopp frenzy of the 1990s, several observatories imposed temporary embargoes to coordinate press releases, citing public confusion from raw, unverified numbers. To some, this looked like prudent caution. To others, it was information control. The question now hangs over Atlas and Swan. Is the restricted flow a matter of coordination, or does the convergence of two anomalous comets on Mars demand a tighter lid than usual? For a growing number of independent observers, the lack of transparency only fuels suspicion that something extraordinary is unfolding just out of view. For planetary scientist Dr. Elena Markovich, the past weeks have blurred into a haze of 20-hour shifts. From her console at the European Space Operations Center, she watches streams of numbers cascade across her screen: orbital solutions, spectral data, tail morphologies. She admits in her private notes that tracking one anomalous comet is exhausting. Tracking two converging on Mars at the same time is something else entirely. In her diary entry dated October 3rd, she writes, "There is a strange duality in this work. We are exhilarated to witness events that no generation before us has ever seen. And yet, every new flare, every outburst, feels like a reminder of how fragile our models really are. We do not predict, we react." Markovich recalls the public fascination with Shoemaker Levy 9 as a child. Now she finds herself living through a scenario with unsettling echoes: two bodies, unstable and unpredictable, approaching another planet's skies. She describes the atmosphere and mission control as electric and tense. Screens flicker with live orbital updates, conversations stretch late into the night, and every software run carries the weight of what if. For her, the double object anomaly is more than science. It is a lesson in vigilance, a reminder that the universe rarely delivers threats or wonders in isolation. They come clustered, chaotic, and relentless. For those watching from Earth, opportunities remain limited but not absent. 3i Atlas is expected to brighten steadily through mid-October, visible in the early morning skies near the constellation Leo. At its peak, observers with medium-sized telescopes may glimpse a faint greenish coma and an elongated dust tail stretching westward. R2 Swan is more challenging. Its brightness fluctuates with sudden outbursts, but at times it reaches binocular visibility in the constellation Virgo. Backyard astronomers with dark sky access may catch its bluish hue and rapidly shifting tail, though these views will depend heavily on timing. Caution is required. Both comets approach solar conjunction, meaning they drift closer to the sun's glare from Earth's perspective. Observers should avoid dangerous attempts to track them near sunrise or sunset. For most, the best strategy will be to follow updates from observatory feeds and amateur networks that report outbursts in near real time. The view may be fleeting, but for those able to spot them, even briefly, the sight of two rare comets converging on Mars offers a chance to witness history with the naked eye. October 2025 has delivered a convergence no planetary scientist expected to see in their lifetime. Two chemically bizarre bodies, the interstellar enigma 3I Atlas and the hydrogen torch R2 Swan, now race toward encounter windows with Mars. Separately, they would have demanded full attention. Together, they defy statistical expectation, forming a pattern that has no easy precedent. The discoveries traced a clear arc. Pan-STARRS spotting Atlas on a hyperbolic path, SOHO's Swan instrument catching Swan in hydrogen flare, and JWST, VLT, and Mars orbiters scrambling to collect every scrap of spectral data. The results shattered assumptions. Carbon dioxide overwhelming water, nickel without iron, hydrogen jets erupting where none should. The timing amplifies the mystery. Both objects peak as Mars enters a solar blackout, leaving ground-based telescopes blind at the very moment of closest approach. Some call it coincidence, others whisper of choreography. The implications ripple outward. For planetary defense, the lesson is clear. Near misses and fragmentations can occur in clusters, not in isolation. For astrobiology, anomalous chemistries hint at formation processes, or selective processes, still unexplained. And for the signal hunters, every unexplained spike in the radio spectrum is another reminder that the universe may carry messages hidden in noise. What we know is this: two strangers in the solar system are converging on one world. What we do not know is why. Natural accident, cosmic choreography, or something built, not born?